All right. Good afternoon, everybody. My name is Kevin. I'm the training coordinator with the Association of State Floodplain Managers. I'd like to welcome you to our quarterly Cooperating Technical Partners Information Exchange training webinar. Today, we're going to be learning about hydrology. And before we get into this exciting topic, I just have a couple administrative announcements to get through, and then we'll get into our agenda. So firstly, I just want to let you all know we have a big group today. We're not going to be able to have lines unmuted to verbally exchange questions and dialogue, but we do want you to participate. If you have questions about anything you see today, if you have a comment you'd like to make, that's all encouraged for sure. I see a lot of you using the chat feature right now. If you have a question you want answered, please find the Q&A feature here within the Zoom software. It's a similar feature to the chat, but not the same. So if you have a question, put it over in the Q&A. If you do use that chat feature to ask a question, it may get lost. So no guarantees there, but we do want your questions. So if you have any, drop it in that Q&A, and we'll take as many as we can kind of as time allows at the end. Next, just want to let everybody know this webinar is, of course, approved for continuing education credits for CFMs. It's also approved for AICP CM credits, so you'll get 1 credit for that as well. The credits will be updated for CFMs, national level CFMs, on your records in about a week. And we'll also be sending out a certificate of attendance via email at that time. So you'll get an email that lets you know we've added the credit to your record. Here's your certificate. If you need it for any other purposes, if you're a planner who needs that credit, I'll give you the event number. You can look that up as well at that time. So it's going to take us about a week. So please be patient, and we'll turn around all that promised follow-up next week. Okay, I think I just mostly went over this. But last note I did want to make is just in terms of like group viewing, if some of you are in small groups or whatever, we cannot track that attendance for all those groups. So it's not eligible for CECs if you're kind of viewing this in a group setting, but still obviously great information to get. So with that, we're going to talk a little bit more about our Cooperating Technical Partners Subcommittee, the work that they do, some of the initiatives of this training series, and then we'll talk a little bit more about our topic and speakers, and we'll be off and running. So for this portion, I'd like to turn it over to Alan Luloff in ASFPM's Flood Science Center. So Alan, go ahead, take us away.
Hello. I'm not sure if it's good morning or good afternoon to people, but hello. And this is the part of the CTP basic technical Cooperating Technical Partners Subcommittee, which was created about 5 years ago. And the co-chairs are Joanna Rolfe and Manuel Razzo. The Dave Gannett was a co-chair for a number of years and has recently turned it over to Manuel. And you can see here the primary goals of the subcommittee. And one of the things ASFPM is very supportive of the Cooperating Technical Partner Program, and our board of directors has passed a resolution in support of that. We were very thankful to have Laura Algio being our FEMA contact on this. She did a great job, and she has recently left FEMA. So again, this is a group that ASFPM is very supportive of. Today's presenters are me just basically giving the introduction, Bill Brown and Mark Forrest. And I've known Bill since about the mid-90s, and Bill worked in the integrated stormwater and floodplain management programs in Lake County, Illinois, DuPage County, Illinois, Greenville, South Carolina, and most recently Arlington, Texas. Uh, he was a researcher instructor with the Biosystems Engineering Department of University of Minnesota, Twin Cities, and instructor of Civil Engineering Department of the University of Texas, Arlington. He's been with ASFPM in the Flood Science Center for over 8 years. And prior to that, he was committee co-chair of the Mapping and Engineering Standards Committee for many years. And he actually, when I was co-chair of that group, he was very active, and that's where I first met Bill. Mark Forrest, he's the Technical Services Director of Water Resources for Consor Engineering. Mark is also a board member on the ASFPM Foundation Board of Directors. He has says approximately 45 years of experience, both in the public and private sector, doing hydrology, hydraulics, floodplain management, FEMA, flood insurance studies for FEMA and communities and CTPs. They both have PEs. Mark is a CFM also. And I guess one of the things with Mark, I just recently went to a training session he had on 2D modeling. He's also very experienced in the 2D modeling world. So with that, I think it's Mark is going to be controlling the slides and turning over to presenting the material, and Bill Brown is starting the presentation.
Okay, that's the title. Obviously, I'm Bill Brown. I'll be going over the first part of the presentation. Obviously, you're here for hydrology and learning the basics. So next slide. So one of the questions that people comes out, when you get out hydrology, you hear the term H&H models. The first H is hydrology or hydrologic, and the second one is hydraulics. We're going to focus on today only on the hydrology, primarily on the hydrology aspect of it, but who uses these models? These professionals that are involved in this include flood managers. It provides information so you can develop flood risk areas and potential damages, because that's the water part. Stormwater managers, obviously rainfall, hydrology, that's stormwater. That will come into play, for flood information, erosion risk, pollutant transport, and it integrates into water quality models. Water utility folks are interested. That's just potentially a source of drinking water. Also comes into play for discharge of treated effluent. Governmental agencies, regulatory oversight of waters in the U.S., environmental resources, recreation, you name it, it all comes into play there. And planners, it helps them develop considerations, risks, and for any kind of amenity or area of interest. So there's a lot of uses for this type of information. But next slide. One of the big things as we deal with this is, what does hydrology really mean? So this is a definition of it, but hydrology is used to determine the amount of flow discharge at any given point for a given event. You try to simulate the processes of the water cycle. Infiltration is, the water going into the soil. Evaporation is the water, going back into the atmosphere. And transpiration is basically the plants, uptake by the plants and back into the atmosphere. There's a lot of other processes, but hydrology is trying to address all of these pieces of the puzzle. Next slide. So here's just one of many graphics of trying to explain all of the pieces of the puzzle of what hydrology is. Every aspect here is, it all kind of is a big cycle. You see it's driven in many different ways, but it basically covers all the aspects that we're trying to model and come up with to get an estimate of how much runoff or discharge is moving through the system. So this is a fairly thing, but one more topic and one more typical aspect of this is the next slide. You see this one? This is one a lot of people see, but it kind of explains how the hydrology changes as land use changes. So if you look in that upper left, you see as precipitation falls on a natural landscape, you're maybe about 10% of it running off. Whereas in a fully urbanized area, looking at almost 5+ times or 6 times more runoff coming. So this comes into play, especially of importance with flood studies. How much water is entering the system that will then derive and create the flood scenarios. So next slide. So what can a hydrologic study give us? It can give us estimates of basically of flow at any point of interest in a specific event. Most people want the peak flow or a hydrograph, and I'll kind of explain what these are, the hydrograph here shortly, but for a specific event of interest, the 1% chance with a 100-year storm, you hear people talking about those things, but they're for many other events of interest. Annual event is usually considered to be a channel forming event. So if you're worried about erosion or how the channels are being formed, that would be typically from a geomorphology perspective is the annual event. Anyone who's interested in water is likely interested in the hydrologic studies or what's going on there next. So when we talk about frequency, what is frequency? Well, it's typically known also, frequency, recurrence interval, or return period. Lots of terms and lots of misunderstandings on these terms. Probably the biggest and most important aspect of it is the 100-year event does not occur every 100 years. First off, it's an estimate. But, if you look at some parts of the country, and I'll use an example of Houston. And Houston has had 500-year floods in 2015, 2016, and 2017. And to add insult to injury, they had a 100-year flood in 2019. So if you do your math, they had under a 5-year window, they had 4 events that exceeded the 500-year, and they had 3 that. So the statistics are the statistics. They're an estimate, but they are a situation where, can't take a lot of. It may be a good estimate, but it's just something that we work with, and probably needs to be updated. So next slide. Data needs for tools and methods. Basically, what do you need to come up with hydrology? Well, watershed, you got to know when it rains or what the precipitation, where's the water coming from? It's probably one of the most important aspects of it is to identify, when the water or when precipitation or anything falls onto the surface, how does it move? Where does it flow to? Topography provides insight as to where the water goes and how fast. Land use impacts, obviously from the earlier graphic, shows how much flow is being generated. It'll provide information. Remember, it's not constant. There are seasonal changes, and there are things that are growing in the channel that may slow the water down. So there's a lot of different factors that come into play from the land use. Soils, the geology are important. Does the soil infiltrate easily, or is the soil stable or erodible? So these are all factors that come in and impact hydrology. The meteorologic data is obviously the fundamental piece because that's the rainfall typically, and so, temperature, evaporation can also have a big impact on snow melt, transpiration, soil dryness, and more. So you got to factor a lot of these pieces into your hydrologic hydrologic models potentially. So structures are related to, basically, what structures are related to the land use, and they come into play more in the hydraulics, but structures do impact how the water moves through the system. Next slide. So I mentioned earlier hydrograph. This is what a hydrograph looks like. A hydrograph is typically describes the flow. On this graph, the upper left corner of the graphic shows rainfall felt, and that gives you a time. If you look at the base of the graph, that's the time in hours. So it rained for a period of time. And notice that this one doesn't start at 0. There's a base flow. So like typically in many streams or rivers, you'll have a base flow that's in there, and anything, the precipitation, the runoff adds to that. So that's why you see that formation here. So basically this is used to calculate the peak flow, to calculate the volume of runoff, and the timing of the water moving through a basin. And this is pretty much the standard that a lot of people utilize and going from there. So next slide. Typically, hydrologic tools or methods come in 3 flavors: statistical analysis, basically analysis of flow records or stream gauges; regression analysis, where analysis of multiple gauges in a region are used to develop an estimate for ungauged watersheds of that area. Typically, these became available, and they've been around for a while. The next one is computer models. Computer models didn't really hit the arena actively until the 1960s, and really didn't evolve until the computers became more accessible to the average user. So, just for those who are in it, it's pretty much the computer side is only about 60 years since they first came into play. The TR-20 was developed by the SCS, now known as the NRCS. That was first created and run on a mainframe in 1964. The PC version wasn't released until 1982. HEC-1, which now many people know as HEC HMS, it was first run on the mainframe in 1968 and became available on a desktop computer in 1984. Next slide. So statistical analysis, basically you take annual peak discharges at a gauge. And this is an example using HEC SSP tool. It's basically statistical package that the HEC tools has made available. And its probability along the bottom of the graph, it equates to the return period along the top axis. Remember, in this one, the red line here is typically used as the median estimate. So basically, there's a 50-50 chance that the estimate is higher or lower than that line. The green lines are the confidence intervals. There's a 5% and a 95% confidence interval. And from there, you basically move on. So if you're looking at this graph, I know it's hard to see and look at it, but the 0.1% probability is actually the 10-year event. And at the 5% confidence interval, that is a 5,000 CFS estimate. The mean estimate, which is the one that's typically used, is 6,500 CFS, and the 95% confidence interval is 7,500 CFS. So this is basically the statistical, what you would get typically using these types of tools, but you need a lot of gauge data to utilize this one. Next slide. Regression equation. This is an example of regression equation developed for Marengo watershed in Wisconsin. There are 6 USGS gauges near the watershed and were used to develop this estimate. Now, if you look at it, you got 6 points on there. The reason you've got 2 curves is because one of them is the 50% or the 2-year event, and the other one is the 1% or 100-year event estimates. So, from there, along the line, you can pick off the size, the area, or the size of the drainage area, run up, know what the 2-year or the 100-year estimates are, and pick that off from the left side of the curve. Pretty standard method. These are relatively, you can go and get this done through the USGS tools, but this is one that's typically been used, has been used a lot up until the further enhancements of the computer models. The final option is the computer model. Here's an example of the U.S. Army Corps of Engineers HEC hydrologic modeling simulation system. So basically, what you do in here, you identify the watershed, subbasins, flow paths, and other features. You work through it, and you can get a hydrograph at all locations, at all points of interest to the stream. It's a much more dynamic, a much more useful tool, because this one does all the dirty work for you once you start the calculation of it. But you can apply rainfall at different rates across the watershed. You can work through many things. So Mark will cover a lot of that, but this is just kind of the basic aspect of it. So next one. Common hydrologic models that are out there are the event-based models. This is basically running a single rainfall event, a model that focuses basically on producing peak discharges, typically a 24-hour event, but you can do critical events that may be shorter or longer durations. So it could be like a 1, 2, 3, 6, 12, 18, 36-hour event. Whatever fits your interest there. Typically, the drainage areas and the travel length impacts are critical event for the critical, drive the critical event, and very few do this level analysis. So the standard is typically the 24-hour event. There are areas, though, that look at what event duration creates the peak discharges in their system. A continuous model is what it implies. It's over a long period of time, historically not used due to the computer processing time, but the technology is changing, and that may change in the near future. So we typically see this more frequently for water quality and water utility studies. So that pretty much, next slide, that takes us up through my portion of it, and there'll be a transition part here, and I'll turn it over to Kevin for a knowledge check.
Yes, excellent. Thank you very much, Bill. That was great. So I forgot to let everybody know up top as part of my announcements, we are going to do a little bit of a knowledge check or a quiz, if you want to think about it that way, just about some of the things we just learned about. So give me a moment and I'll open it up and you'll be able to respond to that in just a moment. Hang on, please. Okay, so you should all be seeing it now. 2-question quiz. Take a minute or two, and then we'll go over the right answers in just a minute. All right, I'll give everybody just a couple more seconds. Okay. So, Mark, Bill, can you see those results there on the screen?
I can see the results from the first one, and it appears the majority of you got it correct. A flow hydrograph is a graphical representation of discharge in time. Basically, it tells you what the flow is in at that point at any given time, and it can be basically, for the storm event or whatever, but it's basically a discharge of flow versus time. Which of the following are not true? Can you scroll that down, Kevin, or can I do that?
I think you can, but most got it. 88% responding C.
Yep.
The 100-year event occurs only once in 100 years.
Yeah, it doesn't. Yeah, that's completely wrong. It's evident by my example of what happened in Houston. So it's clear that just because it was the 100-year event doesn't mean it's going to you can wait 100 years. It can happen again tomorrow. So just be aware of that aspect of it. So
Okay.
With that, I'll be quiet and hand it over to Mark.
Cool. Thank you, Bill.
Thanks, Bill. So hopefully this is transitioning here. Where we go. So we're going to talk about the context of hydrology in the National Flood Insurance Program. And I think there's some basics that are helpful to understand if you're administering a CTP program or a floodplain management program in your community. Hydrologic modeling and analysis can answer a lot of different questions, as Bill talked about. We can simulate and calibrate or validate to actual events, then apply that to a theoretical event to get to the event we're attempting to manage to. There are surface and groundwater interactions that can be simulated. All the things that Bill talked about there, sediment transport analysis. Our models can be used for doing a lot of different things, including evaluation of land use change impacts to quantity and quality with these tools. But in the context of the NFIP, the type of data and the level of accuracy that we historically have used to develop flood hazards in the NFIP are variable depending on the type of hazard identification criteria we're using. So many of our studies in the past have identified areas where we'd want to know that there is some degree of potential hazard, but we don't necessarily need base flood elevations, but we need to have an awareness of where the potential range of floodplain limits are. And that's been done as an approximate zone A designation. So it doesn't contain base flood elevations, and it's based on a very approximate hydrology and oftentimes very approximate topography as well. So the flood limits are questionable in some cases because they're based on both approximate terrain and approximate hydrology. Detailed studies then kick up that level of the standards for both hydrology, hydraulics, and for topographic mapping. So now you're starting to do refinements in each one of those areas to make sure that you're identifying the flood hazards more accurately and the base flood elevations more accurately. We also have special cases in the NFIP for the types of hazards we're identifying. Alluvial fans are a unique type of hazard, and they're identified with a different range of input parameters and tools. If you're dealing with shallow flooding or flooding behind behind a structure, it can be a roadway, for example, that is backing up water because of a culvert, may be defined as AH, where AO is typically shallow flooding, less than 3 feet deep, and identifying the approximate average depth of flooding. Those still rely on more detailed hydrology than an approximate zone A does. And AE definitely requires a higher standard that defines how it also can be revised. So one of the reasons why you're defining those higher standards is it also sets the criteria for somebody wanting to revise it, has to show that their revision is based on better technical information, better data, or superior technical methods. We also use it for risk map products, as I identified in that last bullet. This is a similar graphic to what Bill was showing, the full hydrologic cycle, but we're mostly concerned about those riverine corridors. Typically in the past with the NFIP is what does hydrology tell us about the rate of flow that is going to need to be mapped as a flood hazard in those riverine corridors. Bill talked about regional regression equations, and I want to expand a little bit about on that. It's important to understand that accuracy limitation that he was also describing. It only can be used for approximate hydrology. So zone A, it's not a reliable source if you're attempting to do a more detailed study and you want to assign BFEs. It's not an appropriate tool for that purpose. Because it has much larger error bands associated with it. And one of the reasons why it has large error bands is it's derived from peak flows from just the available gauge record in the area. So you can see in that lower graphic, the gauges are oftentimes pretty highly dispersed, and the watershed characteristics of each of those gauged watersheds varies in terms of land use, soil type, and characteristics of the watershed. And your particular watershed may differ pretty considerably in all of those respects, and therefore trying to draw correlations from a gauged location to an ungauged location has uncertainty that needs to be considered. So there are large error bands associated with that information. Each of the states does publish their own. USGS has typically published these regional studies on a statewide basis. And so you can see what went into those studies by reviewing those documents, and they're updated every so often, typically on a more of a decadal level than annually. And there is also a web application that you can see the URL for at the bottom of the screen that will allow you to generate an estimate at a given location using those tools. Detailed hydrologic studies are used to inform more detailed floodplain mapping, and they can be based upon a number of things, as Bill was also talking about, either gauge statistics, if you've got a representative gauge in the reach of interest, which is rare, but it's only going to be applicable to a short reach of that stream. And as the watershed area either decreases in the upstream direction or increases in the downstream direction, then the results are from that gauge are not going to be applicable. Hydrologic models of the watershed, which Bill talked about, HEC HMS for that purpose. And the newest one on the scene is doing the analysis based on a rain on mesh, which is actually a two-dimensional hydraulic computation where you're applying rainfall to your model domain in order to simulate the response of the entire watershed, not just a single stream reach, which historically is what the NFIP has been based on. So we'll talk a little bit about that and show you some examples. The differences between hydrology and hydraulics, as I think Bill covered this pretty well, but the hydrologic data in the NFIP has historically been is really focused on specific events. So most of the older flood insurance studies published peak flow estimates for the 10, 50, 100, and 500 year return periods. And there's a little bit of confusion about the 10 and the 50, and I'll try to cover that. The volume of runoff oftentimes is a factor in some floodplain hazards, not just the peak. And the example on the screen there is actually a closed basin lake close to me. This is actually a study that I participated in. It's north of Reno. It's a playa. And so when seasonal precipitation is high during the winter period, these lakes fill up, and the probability of flooding is associated with accumulated runoff in that closed basin, because the only way for water to exit is via evaporation. So it's a much more complicated hydrologic problem to solve. And in this case, we actually did use continuous event simulation that Bill was talking about, combined with a stochastic analysis to estimate what the 1% chance lake level would be for that playa. But it's also important to understand in this particular type of hazard, when we deal with flood hazards in riverine settings, the potential damage when the structure is flooded for a matter of hours or less is very different than in this case when the structure is flooded for weeks, if not months, and it usually means a total loss. So why are the 100-year and 50-year events originally included in older flood insurance studies? The reason a lot of people are not aware of is that when the flood insurance program was first initiated, the hazard factors, there were flood hazard factors identified on the flood insurance rate maps referred to as numbered A zones. And those flood hazard factors were used to determine what the flood insurance rates were. So the greater the hazard, the more frequently it would be flooded, the higher the velocity. Other factors were included to determine whether or not a higher rate should be applied. It made it very difficult for the lenders and appraisers to be able to get to assess the appropriate rate for a structure. So that was abandoned for now the AE zone. So flood hazard factors are no longer used in rating policies, and therefore the 10 and the 50 year are not explicitly used except in risk map products. So risk map products are also an important component of the National Flood Insurance Program, and the tools that can be used by a community to do risk mitigation planning, because it develops the information for the more frequent events that a community can use for assessing what the range of hazards are in their community, and provide that as a basis for flood mitigation planning and potential funding associated with those mitigation programs. Detailed hydrologic studies, it's really important to understand is if you're managing a CTP project and you're considering the options for the choice of hydrologic methods when you're doing a detailed hydrologic model, there are different methods that are out there. And one of the things that I teach when I do training to practitioners is that understanding that those methods are really cookbook methods. Those cookbooks are like any other cookbook. When applied the way that they're described, you can make one kind of muffin, but if you need to understand how to vary that recipe because you've got a unique recipe that you want to make or unique product you're trying to make, you need to understand all the interactions that are taking place in order to make sure that you're applying those fundamental tools correctly. So I find that the fundamentals of hydrology are not typically taught to most civil engineers, which is unfortunate. Those are the predominantly the people who are doing these studies, and they may not have had the fundamentals in their their scholastic program, so they're having to learn these things as practitioners as they move forward. We don't invest enough, I don't think, either in hydrologic research like we do in hydraulic tools. So a lot of our cookbook methods are a bit dated, and they're also oftentimes misinterpreted. Common cookbook methods for gauge analysis, we'll talk about those first, is where gauge analysis is going to be limited to where the gauges are located. So not all gauge locations also contain the sufficient data to do a gauge analysis. So that's not always an option. Even if there's a gauge located there, it may not have a long enough period of record, or it may not be collecting peak flow data, or the peak to flow data is not real reliable. Gauges also can be moved by the USGS and still maintain the original name and number, but may represent more than one location. The streams tend to change, as we saw with recent events. The amount of erosion that can take place, the channel geomorphology can change as a result of a flooding event, and that makes maintaining the rating curves that are used by the USGS to estimate peaks also a variable. So it's important to understand that the USGS is not measuring peak flow. They do measure flows at different levels when they're able to get to a site, and that's used to construct a rating curve. But for the peak estimate for a given event, it is derived from that rating curve. It's not a measured value. What they're measuring is stage, the stage time relationship, or a stage hydrograph. And that's converted to a flow using a rating curve that is from measurements over time at lower flows. Cookbook methods for hydrology. There are a number of methods that are commonly used that you may see applied to CTP projects. The curve number method is probably by far the most commonly used method for doing hydrologic modeling. It was developed by the SCS, now NRCS, in the 1950s to support the PL 566 program, which was the construction of detention basins, dry basins, dry reservoirs, typically all over the United States. And they needed a methodology that they could apply nationally that would give them reasonable results for the design of these facilities across the U.S. At that time, we had very limited data available to us, particularly rainfall data and other data. The runoff response is based upon data that was acquired from ARS facilities all over the U.S. For example, the desert shrub data comes from the ARS facility near Tombstone, Arizona, referred to as the Walnut Gulch Research Facility. Sagebrush and grass is from the Reynolds watershed up near Boise, Idaho. So these ARS facilities are scattered across the U.S. and have been collecting very useful data for hydrology for decades. But it leverages the differences in soil type, plant cover type, and the cover density associated with that plant cover, and other types of developed land uses to characterize the runoff response. So as you can see in that picture in the upper right, there's a significant difference in the different surfaces you see in that photo, from the trees in the background to the pavement in the foreground, and the lawn or grass in the shoulder of the roadway. All of those surfaces produce a very different runoff response. And they're characterized in the curve number method with the available data. What is challenging is that the TR55 is the most common cookbook that's referred to, and it reduced the original data developed by Victor Marcus when he did the original studies in the 1950s and 60s as a graphical representation of cover density versus curve number. They reduced to a table. So practitioners often misinterpret that table and also believe that they have to only pick a single value out of that table and not interpolate based on their actual site conditions. And that's where it often gets misapplied. The other method that's commonly used is green and amped. If this is being suggested for one of your studies, you might want to ask a lot of good questions about how they're going to parameterize those models. Green and amped has some advantages over curve number, but also has some disadvantages. It's based on research from the 1920s. It tends to be more physically based, but the common misapplications of green and amped is that oftentimes the practitioner uses only the dominant soil from the soil surveys, and a soil map unit may contain 3 or 4 different soil types, and the dominant soil may not be the highest percentage. So if you don't consider the minor soils, you'll often misrepresent the runoff characteristics of your watershed. And that's true of the curve number method as well. And the green and amp method does not have that same ability the curve number method does for assigning the interception loss associated with the plant canopy, like the curve number method does. So the evolution of our tools for hazard identification are evolving very rapidly. New tools are allowing us to do our work with a lot greater level of accuracy and give us a ton more information with regard to the actual hazards that are occurring even at the watershed scale. So in the first 50 years of the NFIP, we relied on the methods I described and on models that are based on 1D steady flow assumptions. And we're finding with the two-dimensional solutions that are now being applied pretty robustly throughout the NFIP that the 1D models were lying to us about the effect of encroachment, about how flood waves propagate through our system. They have misled us as floodplain managers in a lot of different ways, and 2D models are giving us a very different and much more accurate picture of flow behavior. This being an example of the complexity of flow behavior through these two bridges, and the two-dimensional model is able to identify where those flow separations occur and what the true flow dynamics are when the roadway gets overtopped, and doesn't assume that it's the same water surface across that entire roadway like a 1D model would. So rain on mesh has become a real common for doing basin scale hazard identification. This is an example for a watershed in New Mexico that I tested. We originally did the modeling with HEC HMS, and the question was, what would a rain on mesh model give us a similar answer as HMS did, which you can see in the hydrographs there in the lower left. The rain on mesh HEC RAS 2D model gives us actually a much more accurate answer because the empirical models for in HMS are relying on a unit hydrograph, and there's a lot we could go into a lot more technical detail on that one. But the rain on mesh is simulating the flow propagation in the watershed much more as a physically based response. But the takeaway there is how closely they actually mimic one another with a slight offset in timing. And it gives us information not just at a single point, but everywhere within the watershed. So our historical practices in hydrology, one of the weaknesses we have always had in hydrologic modeling has been how we represent the rainfall in our models. And as you can see from this video, there's the YouTube link down at the bottom if you want to ever go look and watch this again. We'll provide you with that link. But the assumption in most historical models is the rainfall events are stationary. Well, we know from available data through radar and other tools that were limited when the NFIP started to pretty much just gauge data. Now Doppler radar gives us the same picture that you see there of how these storms really truly behave. And it's very rare for a rainfall event to actually be stationary. The moving storm concept is the moving storm outcome is what really happens, and how that affects our simulation of the runoff response is really important. So one of the ways we can do that with current technology is the use of the Doppler data that we can then adjust to gauge data to produce a gridded rainfall pattern for a given event, which allows us then to simulate the response from that watershed compared to gauge data to validate our models and improve our models, but also gives us information about how these storms really do truly behave. And there's a lot of variability in both in time and space for how that rainfall impacts the watershed. So how variable are our rainfall events? This is another key principle that I think a lot of people don't understand, is that the United States is affected by different storm types that produce our flooding outcomes. And each one of those has unique seasonal characteristics and unique differences in the type, in how they affect our watersheds and our floodplains. Monsoonal events mostly affect the Southwest, Texas, New Mexico, Arizona, Southern California, Southern Nevada, Utah, Colorado are pretty heavily impacted by monsoonal events. We've been seeing those in the last few weeks. They've actually pushed up the backside of the Sierra all the way up to Reno in the Lake Tahoe region in the last few days. So sometimes monsoonal events affect that whole quadrant of the U.S. Atmospheric rivers and monsoons occur typically between mid-July and mid-October, so there's a seasonal difference. Atmospheric rivers typically occur between November and March. They cover a much larger area, and they come out on shore along the coast of California, Oregon, and Washington, and then push inland from there. So a lot of our larger watersheds in that region of the country, the largest peaks in the record are typically based on atmospheric rivers, or in response to atmospheric rivers. Tropical events can affect the Gulf of California region, as Gulf of both Gulfs and also the eastern seaboard are affected by tropical events like Hurricane Harvey, Katrina, the ones that we know from the record. Can produce very significant precipitation, not only in the coastal zones, but also push further inland as well, like we saw in the last few years in Appalachians. Tropical events can also affect even the region, the monsoon-influenced region, because the remnants of those hurricanes can push inland enough that as that period of record you see in the lower right is for a gauge in southeastern Arizona. And that gauge, what you see in that data point, the highest data point is actually a tropical event. That was Hurricane Octave. And the next larger event to the right of that was a monsoonal event. And then all the rest of the data points are a combination of both monsoons and atmospheric atmospheric rivers. So it's a mixed population, and there's been some really good recent research on evaluating how do we break this out so that we can identify the real true atmospheric components that are associated with the gauge record, so that we're doing the analysis more correctly. And then there are mesoscale and synoptic scale events, which are the frontal events that go through the U.S. And they can also occur typically in a different season or more than one season. So separating that out by season is important. It affects the scale of the event, how large a watershed they affect, where monsoonal events can often be very small footprint. The rest of those events can tend to have a much larger footprint. So how we apply these to look at basin scale simulations for identifying both pluvial and fluvial hazards has been a push in the National Flood Insurance Program through the BLE program to do rain on mesh at the basin scale to identify where all the hazards are within the entire watershed rather than just along the primary water course. There are 5 different levels to BLE. Starting off with the courses level that would be useful maybe for mitigation planning, but not even for a zone A. start adding detail like incorporating roadways, bridges at road and culverts at roadways, getting the connectivity correct, improving the terrain data, gets you to a B or a C level, which would be approximate zone A. And then when you add additional detail, you can get to a zone AE. So it's a matter of just upgrading the terrain information, the structure information, and other model parameters to get you to the level of confidence that's necessary to support those different mapping types. So the implications for the NFIP is that our tools are rapidly evolving. The standards that we're using for revising and reflecting new are being revised to reflect the new two-dimensional tools at the basin scale and also at the watercourse level. There are standards that are still being undergoing revision to apply those tools to the NFIP, and there's ultimately going to be a need to also update the regulatory standards to apply to these methods as well, because all of the current code in 44 CFR are based upon 1D steady flow models. And so the two-dimensional models give us information that is going to necessitate ultimately that we revise the regulatory framework that we use in the NFIP as well. But that's sometime in the future. And with that, I guess I'll turn it back over to Kevin to facilitate questions.
Okay, great. Mark, thank you very much. We do have a bunch of questions. I don't know if we'll get to them all, but we do have a pretty good balance of time here, so we'll see how we do. We'll kind of try to take them in order in which they've come in. So kind of starting back at the beginning, Devin was asking, how does climate change factor into this training? It seems like it's maybe a bit of a blind spot for anyone doing modern hydrology and floodplain management to not consider that. So Bill, I think you'd indicated maybe you wanted to take that one.
Get my audio back on.
There you go.
Yeah, that one's a little complicated for us. SFPM supports future risk estimates. We've been a strong advocate of the FFRMS, which future flood risk system estimates. One of the challenges is the current administration's executive order. While it has not completely torpedoed that future-looking aspect of it, it does create some issues. We continue to move forward with other aspects of that in supporting ASCE 2424 and ASCE 7-28, both of which are focused on future flood conditions, which are built around this type of hydrology for the future, from the future aspect. Whether or not those will be implemented at the federal or recognized by FEMA in the coming months or years is yet to be determined. But please also remember this webinar is funded by FEMA, so we try to play nice relatively. But we do acknowledge that there are extreme events that are occurring, and much of the analysis and the estimates are based upon older, backwards-looking data that have not been that are not regularly updated. And the point being, in the Houston one, that was what it was at the estimate. And that actually, those storms predated, I think, the release of Atlas 15, which did increase the rainfall precipitation estimates for the Houston area. So those are definitely will be going up. It would be interesting from a gauge perspective to throw in those 4 years worth of data to see how the shift would occur. But that is one of the challenges when dealing with this, especially if you're using older hydrologic data for your NFIP purposes. It may be underestimating the risk. So just be aware of that.
This is Alan. Just one quick addition to that is, when you're developing these maps for siting new development, you're looking at building structures that are going to probably be there for 100 years. And so you want to make sure, that's why we're such a big advocate of looking at future conditions, both at land use, where increased development, as Bill highlighted, is going to cause increased flows. But also we recognize that rainfall intensity is increasing, and that should be factored in where you have that information. Sea level rise is a little easier one because you can monitor that. Increased rainfall intensity is a little tougher one to do, but we think it is very, very important.
Yeah, and again, I'll highlight one aspect about ASCE 2424. While it is a load standard, it's basically structured based upon the type of structure that you're dealing with. There are different criteria for the use of the facility. So residential versus critical facility in that sense. So all that stuff comes into play, but they do afford mechanisms to look at future climate impacts as far as coming up with the load. What is what the load threshold, i.e., load threshold in many types is freeboard, was necessary for that type of structure. So it is a way that ASCE is independent of any federal thing and is adopted at the local level. So it is something that we've been promoting heavily. And I think we've had other CTP webinars on ASCE 24. If we haven't, I'm sure they're pending in the very near future. So.
Okay, great. Thank you, Bill and Alan, for that. So we're going to carry on with Q&A. I also do, while we're conducting this, I want to launch another poll, and it's just if you could just rate the event we've had today, that'll help us kind of calibrate where to go and how to do things differently or whatever. So if you could just drop a rating in there, I'd appreciate it, and we'll continue with Q&A while that's going on in the background. So Valerie's asking, and I don't know if this is an appropriate question. So presenters, you have to tell me if you think you can take this one or not. But can you explain the difference between like flooding generally and flash flooding? Like what defines flash flooding, and how does that rubber meet the road when it comes to hydrology?
Sure, I'll take a shot at that, and Bill can weigh in too. Flash flooding is one of those more commonly used terms in the media to describe an event that has a very quick onset. So oftentimes it's typical of an event that has, typically a monsoonal event that has incredibly intense rainfall in the initial part of the storm. So you get a very rapid response in the stage and the streams in response to that high intensity rainfall that occurs. So monsoonal events typically will drive that type of behavior where you and sometimes the rainfall is occurring in places where you would not even know that it's occurring. When I worked for early in my career, I worked for Pima County Flood Control District in Tucson, and we had a number of deaths from a summer thunderstorm for people who were sunbathing and swimming in the Sabino Falls in northern Tucson. And the thunderstorm, very intense monsoonal event, occurred in the upper watershed on the Catalina Mountains, not even at the location where these people were recreating. It was way up in the watershed, so they didn't even know that it had been raining. So the event, it produced what we would typically refer to as a flash flooding event, really rapidly rising flow rates, and people were sunbathing on the rocks in the falls and were washed off the falls because they didn't know it was coming, and it came out of the canyon very abruptly. So that's a typical reference to that type of behavior that's really associated with really rapidly rising stages. The disaster that occurred here this year in Texas would be another example.
I concur. I mean, it's something that happens very quickly, and you may or may not be able to get warning out to people. But typically, it's flash flooding versus the typical riverine flooding. Riverine flooding, it's coming. It's just more of a thing. You've got time to prepare and take necessary actions. Flash flooding, it's there. I mean, it's occurring quickly, and you may not have adequate time to prepare or seek higher ground. So,
Yeah.
Or even know it's coming.
I mean, and as Mark pointed out, I mean, if you look at some of the gauge records down there for Kerrville in Texas, and then even 10 years ago in Wemberley, the the rise in the rivers there were over 20 plus feet in like 30 minutes, 30 to 60 minutes. So imagine something coming up that fast. That's pretty evident. That's pretty classic flash flooding in a riverine setting. Otherwise, flash flooding, I've seen basically water flowing down streets because you've got something just occurred quickly and all the water's just flowing. It doesn't have anywhere to go, so it just flows because it's overwhelmed the entire system.
Okay, thank you both. That really is helpful. Tawny is asking about something that I have not seen or heard about, but maybe I'm just too new to floodplain management, Bill. But she's saying, are you familiar with the issues that have been happening in Juneau, Alaska? They've had glacial lake outburst floods for the last 3 years in a row. The ability to complete no-rise analysis with these abnormal events is tremendously challenging. What's the best analysis for these situations? Is it 2D modeling or something else? So I don't know if either of you have experience with that type of situation.
I have limited experience with glacial outburst floods. They are very difficult to predict in terms of both time and also magnitude. The amount of water that accumulates in the glacier before the eruption occurs is going to be really highly variable and very difficult to predict. This is also a function of how glaciers are changing as well. There was a really good post on LinkedIn recently of the response on the glacier itself. So there happened to be a camera set up that was doing continuous capture, so you could see the response in the glacier, but not the response of the flood downstream. But these are common phenomenon in Alaska. But they are very difficult to estimate, and their magnitude is extremely variable. So trying to quantify them in terms of their probable magnitude is not something I've seen anybody do any research or try to attempt to quantify.
And I don't have much to add. I mean, I know that I'm aware of the issue, but as far as how you would quantify or how you'd even predict it, it's problematic. It is an issue, though, related to weather conditions evolving that are resulting in, scenarios that have not really, or not very common, but seem to occur frequently now. So
yeah. Well, thank you, Mark and Bill, for taking a stab at that one. We're going to keep rolling with Q&A for a bit here. If you're asking questions and you haven't heard me prompt our presenters, a couple of things might be going on. One, if you're putting it in the chat area, a lot of the questions are going to get lost there. So if you have a question you want to address, pop it over into the Q&A section of the Zoom interface here, and we'll take as many of those as we can. Any that we don't get to, I'll try to get you an answer in writing sometime in the next week or so. Otherwise, Bill, has been in there typing out answers to questions too. So if you asked a question much earlier, go ahead and check back in that Q&A area, and you may already have an answer in writing for that. So thanks for bearing with us on that front. But so anyway, Aaron is asking, is the risk mapper available in communities still using paper maps? And in this case, effective FIS is circa mid 1980s.
The risk map products are not available for all communities, so they would have had to have been funded for that additional work. And if there is risk map products produced, they would typically be on the MSC site, the Mapping Services Center site, for the communities that have those risk map products. But they're different than the regulatory product, if that's what you're asking. If you're asking about digital data versus the older paper maps, there are still some communities that haven't gone through the process of digital modification, digital updates to their original paper maps. They're rare, but there are a few communities out there that still have the separate floodplain and floodway maps too, and that's oftentimes not understood as during the early phase of the program. The floodways were mapped on a different product, the flood boundary map, and the flood insurance rate map only showed the zone, the numbered A zones. When we went to the compressed flood zones and to the update to the digital products, everything was merged into a single product. But the older maps separated the floodway on a separate set of maps. There are a few communities out there that haven't had those updated, and that's something that those communities should push their region to help them get funding for.
And this is Al. I just want to highlight that a lot of these hard copy maps, because they don't have horizontal control, cannot be digitized without causing some warping. And so that is why FEMA's kind of started this base level engineering concept so that any new maps produced have some type of modeling behind them and are not straight digitized from a hard copy map, which warps the map significantly, and it's really not appropriate for using for floodplain management.
Yeah, that was a common problem early in the days when I was originally doing flood insurance studies in the 1980s. We'd have to produce the work maps on a Mylar, and then when we got the final products back and you overlaid the final firm onto the Mylar, they were distorted. Roads didn't match up. The floodplain map did match up very well. So our techniques for mapping the flood zones have improved considerably in the last 20 plus years with GIS and other tools compared to the way we used to do things, which as more of a manual process with a rapidograph on Mylar. So we've come a long way.
Yeah, for sure. All right. Thank you for that. Next question, related to validation and calibration of H&H models with historic storm events. Are you aware of any recommended resources or guidance documents that can be used for rain on mesh or other 2D models? We are finding this a current challenge with incorporating these types of H&H models in our region.
There have been some guidance documents produced by FEMA. So for the last 6 or 7 years, FEMA has had a committee set up that included representatives from the Hydrologic Engineering Center of the Corps of Engineers, some of us from the private sector, as well as many from both NFIP communities and from FEMA and the study and the CTP and the PTS contractors, going through the process of developing technical standards for the application of two-dimensional models in the NFIP, including rain on mesh, doing floodway analysis, what the mapping product should look like. All of those issues have been worked on over the last 6 or 7 years by this committee, and recommendations made to FEMA that went into those guidance documents. There's still some work to do. I don't think we're entirely there. I think there's a lot of exploration of the use of these tools and some additional modifications of the standards that will be forthcoming in the future. But some of those standards and some of that guidance is already out there, and you can find it on the FEMA website.
Okay, excellent. Thanks. Oh, I'm sorry, I lost my place. Here we go. Okay, Matthew is sort of wondering if anybody can explain the extent to which FEMA flood studies capture inland stormwater flooding. And Matthew says that he's gotten various answers to that, so he's wondering if you're able to weigh in.
FEMA typically uses a cutoff of a tributary point of 1 square mile. So you have to have 1 square mile of tributary area feeding to a point for it to basically start mapping it. In an urban setting, it's pretty difficult to identify 1 square mile of drainage in that sense. So that's why you don't see a lot. If you need an example, go on the Map Service Center's viewer and go to look at the city of Chicago. The only thing there are basically the canals and a few streams. The entire city of Chicago has virtually no floodplain, period. Even though it's it's got lots of issues. It's not uncommon for any other place. It is not unable to have that mapped. It can be mapped, and it has been mapped at a much lower resolution, but it was all done by the local community at their expense.
That is where the BLE product does come into play, though, is that if you know you have those hazards and FEMA is willing to fund a BLE study for your community, it could be incorporated into the risk map products, which are non-regulatory. But if it identifies significant hazards in an urban setting, there could be justification for making that a regulatory product as well. But that's the value of the rain on mesh basin scale analysis is the urban setting is one of those examples where it applies really well and can identify the hazards much better. It does require that the analysis incorporate a fair amount of detail, and I didn't include one of those graphics in my presentation, but I have some of flooding in an urban setting. It's really complex where the flow is trying to move around buildings and down streets. But it's also important to note that the current version of HEC RAS 6.7 is still beta, but it has storm drain capability within it. So it also incorporates the ability to have the subsurface flow incorporated into that urban setting analysis. It's still a work in progress, and the inlets are the part that still needs a little bit of work. But it's a really good start at being able to do a much better job in an urban setting of identifying flood hazards.
Yeah. Okay. Thank you for the thorough response there. That was really helpful. Tyson says, you mentioned that hydrology still relies on limited current research and older methods. Given that we're living in an era with unprecedented data availability and advanced analytical tools, what do you think are the main barriers preventing the field from leveraging those modern resources? Is it funding, technical challenges, or something else entirely? So I know maybe it would require you to speculate a little bit, but I'm wondering what you think about that.
Yeah, it definitely requires some speculation, and I'm sure Bill's got some input on this one too. But there has been some research done by some agencies. For example, the NRCS funded research through the U of A, and you can find it out there on the web for evaluating the curve number method, and potentially even considering the green and amp method as a replacement in the NRCS guidance documents. They concluded the curve number method is still their preferred approach due to limitations in the green and amp method for assessing vegetative type and cover density. But they have done some research on the differences, some of the things that were not looked at in detail with the original research that was done by Victor Marcus and his staff. And particularly in the Southwest, where we get these more front-end loaded convective events, There's some recommendations that Richard Hawkins has made for how you modify the curve number method for those types of settings. Currently working on a project in Moab, Utah, where we've had to use some of that guidance that Hawkins has come up with, because the storms are very much front end loaded. The peak rainfall occurs in the first 15 minutes of the event, so the initial abstraction assumptions of the original curve number method are really not applicable when you're dealing with that kind of a setting.
My response to the question is yes. Pretty much all the things you pointed out. It's money, it's time,
Money.
it's and again, realize as I pointed out, a lot of these types of models really didn't come into play until about 60 years ago. So a lot of it is newer technology, and a lot of people are just not that familiar or comfortable with it. And doesn't have the necessary, they don't have a lot of faith in it because they don't know how it works. So as time evolves, yeah, things will get there. I can remember, if it wasn't all that long ago, 25 years ago, if you were running an unsteady hydraulic model, you were radical and FEMA was going to chase you out of the room. You were the Antichrist. So I mean, nowadays it's just like a standard methodology. So time does it evolves. It's just the hydrology side hasn't picked up. But you got to remember, for all those years, FEMA never updated any of that hydrology, or they very rarely updated hydrology. So now that they've become more aware of it and things are evolving, they're catching up. So time will tell.
And another thing to note too is that the curve number implementation in HEC RAS for rain on mesh simulations using the curve number method has a couple of adaptations that take advantage of the research that Hawkins did. You can alter that initial abstraction ratio to utilize his guidance. And you can also include a steady state infiltration rate, so you can model events that are longer than 24 hours long, which was a limitation of the original method. So there has been some improvement, but it just doesn't get as much attention and funding for research as hydraulics has.
Right. Yeah, that all makes sense. Thank you, Mark, and thanks, Bill. Yeah, so Bill, speaking of kind of that slow march of progress in this space, Caitlin was asking, do you anticipate 2D hydrology and hydraulic modeling being required by FEMA instead of 1D in the future for flood studies?
Yes, that's where it's going. That's definitely
I
where
would
it's going.
say that's where it's going, but I also know that, like I said, 25 years ago, 1D unsteady, they said over no way in hell over our dead bodies. So they're all still alive. So at least most of them. So it did evolve, but it just takes time. But one of the biggest challenges at that level, though, is the local communities having the resources or the knowledge or the local knowledge base to understand and review and assess those models. It's all part of just updating and getting people trained to know how to deal with and understand. Alan's working on a project. Alan, who you heard earlier, he's working on a project for FEMA to basically provide guidance to locals on how to what are the appropriate questions to ask about your 2D models and how to assess and review the information. So it is a long process, but I do see the evolution where that'll ultimately be where everything's at.
Okay, great. Thank you. Ty has a question, and I think it might be maybe biting off more than we can chew, but maybe we'll have some key insights. We'll see. How do you recommend small local agencies update their outdated methods for small system sizing versus looking at hydrology and hydraulics at a more risk-based approach? So do you have anything that maybe smaller local agencies can implement their work?
I mean, one of the first things you can do is track where all your problems are. I mean, it's amazing. I worked in local government for over 25 years. Every place I went to, nobody tracked where the flood losses were. And they didn't want to know because then they felt there was an expectation you would be fixing them. But, part of the thing is, you can't fix anything if you don't know what it is and where it's at. So, from that standpoint, there are, depending on where you're at, there are potentials for grants. Now, that is not as great as it used to be, but when I was in Texas, the state of Texas offered planning grants to communities to do just that. Granted, you had to. It was competitive, but they were always commented that they had difficulty getting communities to apply. Conversely, for the FEMA, once you know what the issues are, how do you fix them or address them? It's hopeful that FEMA will still be around, and those mechanisms like BRIC or other ones that will give up small communities those opportunities to address and meet the needs to reduce the risk for their citizens.
Okay. Yeah, excellent. Thank you, Bill, for weighing in there. So we do have quite a few open questions still. I can tell we're not going to be able to get to them all. Like I said, in about a week, when we send out certificates of attendance and things like that, we will endeavor to get answers to some of these in writing as best we can. So be on the lookout for follow-up Q&A documents to come with some answers there. But we'll try and take maybe one or two more and then wrap up a couple minutes ahead of schedule. So Joseph was asking about stormwater management infrastructure. And I apologize, Mark and Bill, if this was already touched on in the presentation. But Joseph saying, do hydraulic models factor stormwater management infrastructure in urban or suburban environments, and whether if they function or fail and relieve or intensify flooding conditions?
You can make the model do whatever you want it to do. I mean, that's a pretty flippant response, but from generally speaking, if you incorporate into your system that there's a structure there, you'll have to provide, information on it. So that could be, basically, say it's some type of pond or detention facility. You'll have stage storage discharge information you'll have to provide. It always assumes that it operates the way it was designed. If it doesn't, you may have to modify that or make assumptions. Similarly, if that fails, it overtops, washes out, whatever, you're not going to know that unless you analyze it. I mean, probably the best example, if you have a dam somewhere, typically, depending on the level of the dam, from the security standpoint, you'll have to do a dam safety or dam failure analysis. It's not reflected in your flood studies. That's a dam failure scenario. And, typically that information is not readily made public. So that's up to the communities to kind of figure out how they deal with that. But yeah, you can pretty much, and Mark can pile on or just do whatever from there. But yeah, you can do it. It's just, you have to think about it.
Yeah, okay, great. I think we'll wrap there. As I said, we've got a few questions, many of you asking for certain resource links and things like that. So just again, be on the lookout for some follow-up from me after this event with some of those responses.
If I could interrupt for a second,
Yeah,
Kevin.
please. Sorry about that, Mark.
I see one question
Yeah.
here that I think would be of general interest and important probably to address is is Jennifer's question on use of Doppler radar data. It's not well understood a lot of times how useful that data is, but particularly as the radars have gotten updated in recent years to a pretty high resolution, very high resolution radar. It is limited to what it can see, so you can have beam blockage from buildings and mountains that limit what it can see. But if you've got a clear view from the radar, it's doing a sweep every 5 minutes. So it's giving you data from every portion of the storm that it can see at a certain angle every 5 minutes. And that comes back to the radar and is recorded as what's called reflectivity data. Converting the reflectivity data to a rainfall depth is a process where you use the gauge data to correlate reflectivity to rainfall depth. That allows you to convert that rainfall or that reflectivity, every single value you get back from the Doppler can be converted to rainfall depth. And so it gives you a spatial and temporal representation of the storm event at pretty decent resolution. So we use that quite a bit for reconstructing events for model calibration. For example, I used it to reconstruct the Hurricane Harvey outcomes for the San Jacinto River, and we were able to match gauge data really well, and both the rainfall gauges and stream gauge data using that information. So it is a process that takes a bit of an effort, and it requires somebody with the right skill set to do that, but the data is all there for making that correlation.
Okay, fantastic. Well, thank you, Mark, for jumping in and handling that one. That was really useful. Yes, we're going to wrap up there. Once again, everybody, look out for an email from me next week with a lot of the follow-up that we've been talking about. Mark, Bill, Alan, thank you all very much for being generous with your time and kind of giving us the rundown on our topic today. And then to our attendees as well, thanks so much for joining us. This is a quarterly webinar series, and we typically make the registration announcements via email. So as always, keep an eye on your inbox for the next announcement. Thanks again, everybody. Have a great rest of your week. Take care.